A new government report is raising eyebrows across the country, especially among anyone interested in extraterrestrials.
It moved too fast to be bound to the sun. Very first object that we have found coming to us from interstellar space, from other places.
In October 2017, astronomers detected a mysterious object hurtling through our solar system at an extraordinary speed, named Oumuamua, which means scout or messenger in Hawaiian. This object was the first known interstellar visitor to pass through our cosmic neighborhood. Its discovery marked a groundbreaking moment in astronomy, as it defied every conventional explanation.
That we detected in space that you believe could possibly have been extraterrestrial.
And now, in a shocking revelation, NASA scientists warned that the object appears to be moving toward Earth again, exhibiting strange and inexplicable behavior that urges us to uncover its truth before it's too late. Could this be our first encounter with advanced extraterrestrial technology? Or is there a natural explanation for this cosmic enigma? All this and more will be discussed in today's episode. From the moment Oumuamua was detected by the Pan-STARRS-1 telescope in Hawaii, it was clear that this was not your average space rock. For one, its speed and trajectory indicated that it had entered our solar system from another star system, distinguishing it from typical asteroids or comets. Initial observations suggested it was an elongated, cigar-shaped object, measuring about 800 meters long, but only about 80 meters wide. Unlike most celestial bodies we are familiar with, Oumuamua did not have the typical characteristics of a comet, such as a visible tail. It was dark and appeared to be rotating as it sped through space. This raised the first of many questions. If it wasn't a comet, and it didn't resemble a typical asteroid, what was it? Further observations only deepened the mystery. Oumuamua's rapid speed suggested that it wasn't bound by the sun's gravity, like most objects in the solar system. Its trajectory showed that it was following a hyperbolic path, which meant it was only passing through the solar system on a one-time visit. But just when scientists thought they had started to understand Oumuamua, it threw another curveball. After it passed closest to the sun and began to head away from our solar system, it did something completely unexpected. It sped up. Comets, as they pass near the sun, tend to accelerate due to the release of gas from their icy cores, a process known as outgassing. However, Oumuamua showed no signs of such activity. There was no visible gas or dust being expelled, but it inexplicably accelerated. This unexplained boost in velocity stumped astronomers. If it wasn't outgassing, what could be causing it to change its speed and direction? Some scientists speculated that it could be an entirely new type of celestial object, possibly made of materials that are unfamiliar to us, or perhaps an ultra-thin fragment of a larger body. Others proposed more far-fetched ideas, including the possibility that Oumuamua could be an alien probe or spacecraft, equipped with a propulsion system we have never encountered before. Harvard astrophysicist Avi Loeb suggested that its thin, flat shape could be the result of it being a light sail, a type of propulsion system that uses radiation pressure from stars to accelerate spacecraft. According to Loeb, this could explain both the object's unexpected acceleration and its strange shape. This theory sparked heated debates within the scientific community. While some astronomers were open to the idea of Oumuamua being an alien craft, others argued that there was no conclusive evidence to support this claim. The lack of communication signals, or any form of technology detectable by our instruments, pointed more toward a natural origin. Nonetheless, the question remained: what kind of natural object could behave in such an enigmatic way? Some researchers suggested that Oumuamua could be a chunk of hydrogen ice, which might explain the lack of visible outgassing, since hydrogen is difficult to detect. Others proposed that it might be a shard of debris from a larger interstellar object that had been destroyed in a violent cosmic event. As Oumuamua moved further away from the sun and out of the inner solar system, most astronomers assumed it would continue its journey back into the vastness of interstellar space. However, recent observations have shown that instead of following the expected path, the object appears to be gradually altering its trajectory. This shift, though subtle, has led to speculation that Oumuamua might be heading back toward the Earth. This possibility has ignited a wave of excitement and concern. If Oumuamua is indeed changing its course, what could be causing this alteration? Is it reacting to unknown forces or gravitational influences within the solar system? Or is there a more complex explanation at play? One theory is that Oumuamua could be caught in a gravitational resonance with one of the larger planets, causing it to adjust its path. However, the more tantalizing prospect is that it may be under some form of intelligent control, slowly maneuvering its way closer to Earth. This would lend support to the idea that Oumuamua is not merely a piece of space debris, but rather an engineered object designed by an advanced civilization. But could this object, initially dismissed as a random interstellar visitor, actually be a reconnaissance mission from an extraterrestrial civilization? And if it is heading toward Earth, what does that mean for humanity? While these scenarios might sound like something straight out of a science fiction movie, the reality is that astronomers are taking this phenomenon seriously. Observatories around the world are continuing to track Oumuamua's movements, searching for any clues that might help unravel the mystery. If Oumuamua is indeed on a course that will bring it closer to Earth, there is still no need for immediate alarm. The object, though strange, does not appear to pose any direct threat to our planet. Even in the event of a close approach, its small size and high velocity make a collision highly unlikely. However, the mere possibility of a close encounter with a reconnaissance tool from an extraterrestrial civilization would certainly be a big deal. What would happen if we actually made contact? The short answer is that it would be an unprecedented, transformative moment for humanity. But is that good? Well, probably not. Stephen Hawking, one of the most brilliant scientific minds of the 20th and early 21st centuries, often compared potential alien contact to the encounters between indigenous peoples and European colonizers during the Age of Exploration. When Christopher Columbus and his fellow explorers arrived in the Americas, they brought with them new technologies, but also disease, violence, and exploitation that devastated the native populations. Hawking feared that if humanity encountered a more advanced alien civilization, we might suffer a similar fate. He believed that any civilization capable of interstellar travel would likely be far more technologically advanced than us. Just as the indigenous people of the Americas were no match for the European colonizers, humanity might be vastly inferior to an alien race, both in terms of technology and power. In his view, the consequences of such an encounter could be catastrophic. Advanced aliens might not have benevolent intentions. They could view humans as little more than a primitive species to be exploited for resources or worse. Even if they didn't intentionally destroy humanity, their very arrival could upend our world in ways we cannot predict. One framework that complements Hawking's warnings is the dark forest theory, which was popularized in the science fiction novel The Dark Forest by Chinese author Liu Cixin. According to this theory, the universe is like a dark forest, where every civilization is a hunter. Each civilization hides in fear because it knows that other civilizations might be out there, and if they are detected, they could be eliminated. In such a hostile environment, the best strategy is to remain silent and avoid attracting attention. Hawking's warnings align with this idea. He pointed out that any civilization capable of contacting us is likely far more advanced, and thus could pose a threat. They may not be hostile by nature, but the mere fact that they have the power to harm us, whether intentionally or unintentionally, makes the situation dangerous. In this dark forest, humanity would be wise to remain quiet and avoid broadcasting our presence to the cosmos. Another point that Hawking raised was the unpredictability of the nature of advanced alien civilizations. While many hope that intelligent aliens would be peaceful and curious, like ourselves, Hawking believed that assuming their benevolence was a dangerous gamble. Civilizations that have developed the ability to travel between stars may have done so for reasons that are incompatible with our survival. For instance, an alien species might be driven by a desire to expand, conquer, or exploit. Given that Earth is rich in resources such as water, minerals, and even biological diversity, These aliens might view our planet as a potential target for colonization or extraction. Just as humans have often exploited weaker species and environments for their own benefit, advanced extraterrestrials might do the same to us. Moreover, we have no way of knowing how aliens might view humanity. They could see us as an inferior species, comparable to how humans view ants or other animals. They might not even recognize us as intelligent life, or they might consider us a threat to their own safety. In any of these scenarios, the consequences for humanity could be devastating. Hawking's concerns also tied into one of the greatest puzzles in modern astronomy, the Fermi paradox. Named after the physicist Enrico Fermi, the paradox questions why, given the vast number of stars and planets in the universe, we have not yet detected any signs of alien life. If intelligent civilizations are common, where are they? One possible explanation, according to Hawking and others, is that advanced civilizations tend to self-destruct before they reach the stage of interstellar communication or colonization. This could be due to wars, environmental collapse, or technological accidents. However, another possibility is that civilizations that broadcast their existence are quickly detected and eliminated by more powerful alien forces. In this context, the lack of communication from extraterrestrial civilizations could be seen as evidence that it's safer to remain silent. Hawking speculated that the reason we haven't heard from aliens could be that they're intentionally hiding. Just as humans might avoid shouting in a dark forest full of potential predators, other civilizations could be keeping quiet to avoid detection. If this is the case, then humanity's own attempts to broadcast our presence could be putting us in danger. Of course, this is a wholly speculative thought exercise, driven largely by our own imaginations and our knowledge solely of past events that have occurred here on Earth. However, regardless of whether intelligent aliens exist, regardless of their malevolent or benevolent intents, one fact remains undeniable. For all the problems we have on planet Earth, some self-created, some from external pressures, there is no evidence that anyone else is coming to save us. No one is coming to solve our energy problems, our resource management problems, our unsustainable treatment of the environment, or problems like war, hunger, nutrient deficiencies, or water insecurity. No one is going to help us value the lives of one another, or even our own lives. If we hope to be saved from the problems facing us today, we have to look inward, to ourselves, and outward, not to the stars, but to one another. In all the world, the greatest resource we have is the cumulative knowledge we've gleaned and the ability to work together. The ingredients are there, but it's up to us to put them together and use them for the good of all. If we want to change the trajectory of our species, seeking knowledge and searching for the true answers to our deepest questions is certainly an essential part of the solution. Thus, regardless of whether Oumuamua turns out to be a natural or artificial object, its presence in our solar system offers an unprecedented opportunity for scientific discovery. If it is an interstellar rock or fragment, studying it could provide valuable insights into the formation and composition of planetary systems beyond our own. By analyzing its material properties and behavior, scientists could gain a better understanding of the processes that shape distant star systems. On the other hand, if Oumuamua turns out to be an alien probe or spacecraft, the implications would be even more profound. It would be the first confirmed contact with an extraterrestrial civilization, a moment that would change the course of human history forever. The knowledge we could potentially glean from such a discovery, whether technological, biological, or cultural, could be invaluable. Indeed, if Oumuamua is an alien probe, it would likely represent technology far beyond what humanity currently possesses or can even comprehend. The probe would be the product of a civilization that has mastered the challenges of interstellar travel, a feat we have only dreamed of. Our fastest spacecraft, the Parker Solar Probe, travels at around 430,000 miles per hour. But at that speed, it would still take over 6,000 years to reach the nearest star system, Alpha Centauri. An alien civilization capable of sending probes across interstellar distances would have solved many of the barriers that currently hinder our exploration of the cosmos, such as energy constraints, propulsion limitations, and life support systems for long-duration missions. If we were able to study Oumuamua up close and verify it as a probe, the first step would likely be attempting to reverse engineer its technology. Could we learn how this probe was powered? Could it teach us how to travel across vast distances of space in a fraction of the time it currently takes? Perhaps it uses a form of propulsion that manipulates gravity or space-time itself, unlocking secrets of physics that are still theoretical to us. Discovering such technology would be akin to how human societies advanced from the horse and cart to the automobile, or from the steam engine to nuclear power. This technological leap could solve many of humanity's pressing issues, such as energy shortages, climate change, and resource scarcity. If the probe operates using some form of clean, sustainable energy, understanding its power source could usher in a new era where fossil fuels and pollution become obsolete. Propulsion systems could potentially allow for colonization of distant planets, mitigating overpopulation and resource depletion on Earth. Moreover, the implications for defense and international relations would be vast. A spacecraft capable of crossing interstellar distances could theoretically be weaponized, raising concerns about the balance of power on Earth. Nations would race to secure control over the technology, leading to potential conflicts or unprecedented cooperation, depending on how humanity reacts to such a world-altering discovery. In addition to technological revelations, a probe from an alien civilization might carry biological or bioengineering information. It could provide us with the first direct evidence of extraterrestrial life forms, even if only in the form of biological signatures, genetic material, or artificial life. The mere existence of such a probe would be proof that life exists beyond Earth, ending centuries of speculation and philosophical debate. If the probe contains data or samples from the civilization that sent it, it could offer insight into the biology of extraterrestrial organisms. How do these organisms differ from life on Earth? Do they share any fundamental biological traits, such as DNA or cellular structures, or are they based on entirely different biochemical principles? Answers to these questions would expand the field of biology in ways we cannot yet fully grasp. Moreover, understanding alien biology might provide solutions to some of humanity's greatest medical challenges. The biological systems that have allowed extraterrestrial life to survive in environments different from Earth's could offer clues for enhancing human longevity, curing diseases, or adapting to harsh environments. What if these beings have overcome cellular aging, effectively making them immortal? What if they've eradicated diseases that we still struggle with, like cancer or viruses? The knowledge we could gain in medicine and biology could extend human lifespans, enhance our resilience to extreme environments, and unlock entirely new fields of biotechnology. Perhaps the most profound implications of all would be cultural and philosophical. The confirmation that we are not alone in the universe would force humanity to reevaluate its self-perception. For centuries, humans have looked up at the stars and wondered if we are unique. Contact with an alien probe would definitively answer that question, prompting a shift in our collective worldview. Religious and philosophical systems would likely face challenges as they attempt to reconcile their beliefs with the existence of intelligent extraterrestrial life. Some religions might see this discovery as a validation of their doctrines, while others might struggle to incorporate this new reality. Philosophers would debate the ethical and existential questions raised by our new understanding of the universe. If there are other intelligent beings out there, what does it mean to be human? Are we still special, or are we just one of many civilizations scattered across the cosmos? Human culture would also be transformed by the knowledge and ideas brought forth by an alien civilization. Even if we could not directly communicate with the civilization that sent the probe, its existence alone would broaden the scope of human imagination. We might develop new art forms, literature, and philosophical ideas inspired by the existence of extraterrestrial life. Just as the Renaissance was fueled by the rediscovery of ancient knowledge, the discovery of an alien probe could spark a new era of cultural and intellectual flourishing. The probe might contain records of its creator's history, art, and culture, providing a glimpse into the values, beliefs, and achievements of a civilization that developed independently from humanity. understanding their culture could lead to a greater appreciation for diversity and the vast potential of sentient life in the universe. Alternatively, it might highlight commonalities, such as a shared drive for exploration, curiosity, or survival, reminding us that despite our differences, there are universal aspects of intelligent life. Moreover, the discovery of an alien probe would also have far-reaching political and social consequences. It would force nations and international organizations to reconsider their priorities, potentially uniting humanity in a way that few events in history have done. Faced with the reality of intelligent extraterrestrial life, humanity might finally set aside its internal conflicts to focus on understanding and preparing for contact with another civilization. There would likely be calls for greater international collaboration in studying the probe and preparing for future interactions with extraterrestrial beings. Space agencies around the world, such as NASA, ESA, and CNSA, would need to pool their resources and knowledge to decode the probe's purpose and origin. Nations that currently compete in the space race might be compelled to cooperate, realizing that the discovery of extraterrestrial life transcends national borders. Socially, the discovery could spark a renewed interest in science, space exploration, and education. The excitement generated by the knowledge that we are not alone in the universe could inspire the next generation of scientists, engineers, and thinkers to push the boundaries of human knowledge even further. Schools might see an influx of students eager to study astronomy, biology, and engineering, all driven by the dream of understanding and exploring the cosmos. However, this discovery could also have destabilizing effects. Some groups might react with fear or hostility, viewing the probe as a potential threat. Conspiracy theories could proliferate, and governments would likely face pressure to be transparent about what they know regarding the probe. The existence of advanced alien technology could also lead to a new arms race, as nations scramble to harness extraterrestrial technology for military purposes. The balance of power on Earth could shift dramatically, depending on which countries or groups gained access to the alien probe's secrets. In the long term, the discovery of an alien probe would likely mark the beginning of a new chapter in humanity's relationship with the cosmos. If Oumuamua is indeed a probe, it might be one of many sent by a distant civilization, and its discovery could be the first step toward direct contact with intelligent extraterrestrials. This prospect raises profound questions. Are we ready for such contact? What would we say? How would we ensure that this encounter is peaceful and mutually beneficial? Ultimately, the discovery of an alien probe would force humanity to think beyond the confines of Earth. It would challenge us to look outward, not just as individual nations, but as a species, united in the quest for knowledge and understanding. We would need to prepare for the possibility that other civilizations are watching us, studying us, or even awaiting our response. How we choose to respond to this discovery could determine the future of humanity for millennia to come. After all, Oumuamua's visit has already spurred renewed interest in the search for interstellar objects and alien life. Fascinatingly, since its discovery, astronomers have detected another interstellar object, 2I Borisov, which displayed more typical comet-like behavior. However, Oumuamua remains unique in its characteristics and enigmatic behavior. Looking ahead, scientists are developing new telescopes and observational tools that will allow us to detect and study more interstellar objects. One of the most promising new tools in the search for interstellar objects is the Vera C. Rubin Observatory, located in Chile, which is expected to begin full operations in the mid-2020s. Central to this observatory's mission is the Large Synoptic Survey Telescope, or LSST, which is designed to scan the entire visible sky every few nights, capturing wide-field images of vast sections of space. This rapid and comprehensive surveying capability is crucial for detecting transient phenomena, including fast-moving interstellar objects. The LSST's ability to survey large portions of the sky repeatedly means that it can identify moving objects by comparing images taken over several nights. This will make it easier to spot small, dim objects like interstellar objects that are quickly moving through our solar system. The observatory's wide field of view, combined with its high sensitivity, will give astronomers an unprecedented ability to detect interstellar objects shortly after they enter the solar system, providing more time to study them before they leave again. In addition to improving interstellar object detection, the Rubin Observatory will contribute to the broader understanding of small bodies in our solar system, including asteroids and comets. Many of these objects share characteristics with interstellar objects, and studying them can provide valuable insights into how interstellar objects may form and evolve in their own star systems. While the Rubin Observatory will play a key role in detecting interstellar objects from the ground, space-based telescopes offer several advantages in studying these objects once they have been identified. One such telescope is the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s. This NASA mission will feature a wide-field infrared survey instrument capable of capturing detailed images of large areas of the sky in the infrared spectrum. Infrared observation is particularly important for the study of interstellar objects because many of these objects may not reflect much sunlight, making them difficult to detect using visible light alone. However, all objects emit some amount of infrared radiation due to their temperature, even if they are dark in the visible spectrum. The Roman Space Telescope's infrared capabilities will allow it to detect and study interstellar objects that might otherwise go unnoticed. By observing interstellar objects in the infrared, scientists will be able to gather information about their composition and physical characteristics. For example, infrared spectroscopy can reveal the chemical makeup of an object's surface, providing clues about its origin and the environment in which it formed. This will be particularly useful for distinguishing between interstellar objects that originated in different star systems or regions of the galaxy, potentially offering insights into the diversity of planetary systems beyond our own. Elsewhere in space, while the James Webb Space Telescope was not specifically designed to detect interstellar objects, it has the potential to make significant contributions to their study. Webb's advanced infrared capabilities, combined with its ability to take extremely detailed images, make it a powerful tool for observing interstellar objects once they have been detected. One of the key strengths of James Webb is its ability to analyze the light spectra of objects in space, which can reveal their chemical composition and other physical properties. If an interstellar object is detected in the solar system, the telescope could be used to perform detailed spectroscopic analysis, helping to determine its origin and composition. This could provide critical data for understanding how planetary systems form and evolve in different parts of the galaxy. Furthermore, James Webb's sensitivity to faint objects makes it well suited for studying interstellar objects that are far from the Sun and difficult to observe with ground-based telescopes. By combining data from James Webb with observations from other telescopes, scientists will be able to build a more complete picture of the physical and chemical properties of interstellar objects, shedding light on their origins and their journey through the galaxy. In addition to detecting and observing interstellar objects from Earth and space-based telescopes, scientists are also exploring the possibility of sending spacecraft to intercept and study these objects directly. One such concept is Project Lyra, a mission proposed by the Initiative for Interstellar Studies. Project Lyra aims to design a spacecraft capable of intercepting an ISO and gathering data about its physical and chemical properties. Interception missions like Project Lyra face several significant challenges, particularly due to the high speeds at which interstellar objects travel. To intercept an object like Oumuamua, which was traveling at 87 kilometers per second, a spacecraft would need to be equipped with advanced propulsion systems capable of matching or exceeding those speeds. Several propulsion technologies have been proposed for such missions, including solar sails, ion drives, and nuclear propulsion, but none have yet been fully developed for use in an interstellar object interception mission. If successful, an interception mission could provide a wealth of data about the internal structure and composition of an interstellar object. Unlike telescopic observations, which are limited to analyzing light reflected or emitted by an object, a spacecraft could carry instruments capable of directly sampling material from an interstellar object's surface, providing a much more detailed understanding of its makeup. In addition to studying the physical properties of interstellar objects, Interception missions could also investigate whether these objects carry organic molecules or other building blocks of life. If interstellar objects are found to contain organic compounds, it could provide evidence that the building blocks of life are widespread throughout the galaxy, potentially supporting the idea that life could exist on other planets or moons. In addition to developing new telescopes and planning future space missions, scientists are also working on a variety of technological innovations to improve the detection and analysis of interstellar objects. These include advanced algorithms for identifying fast-moving objects, improved techniques for analyzing spectral data, and new methods for tracking interstellar objects over time. One of the key challenges in detecting interstellar objects is identifying them against the backdrop of other objects in the sky. To address this, astronomers are increasingly turning to machine learning and AI to analyze large data sets of telescope images. By training AI algorithms to recognize the characteristics of fast-moving interstellar objects, scientists can automate the process of detecting these objects, allowing them to be identified more quickly and accurately. Machine learning algorithms can also be used to track interstellar objects once they have been detected, predicting their future trajectories, and helping scientists plan observations or missions to intercept them. This is particularly important for interstellar objects, which often pass through the solar system quickly and may only be observable for a short period of time. Once an interstellar object has been detected, the next challenge is studying its composition and physical properties. One of the most important tools for this is spectroscopy, which allows scientists to analyze the light reflected or emitted by an object to determine its chemical makeup. Recent advances in high-resolution spectroscopy are making it possible to perform more detailed analysis of interstellar objects than ever before. By studying the spectral lines produced by different elements and molecules, scientists can determine the composition of an interstellar object's surface, its temperature, and other key properties. This information can help scientists understand where an ISO came from and how it formed, potentially offering clues about the conditions in other star systems. In conclusion, as scientists continue to develop new telescopes, observational tools, and spacecraft, the study of interstellar objects is poised to become a major area of research in the coming decades. With improved detection capabilities, more detailed observational data, and the possibility of direct interception missions, the next generation of interstellar object research will help answer some of the most fundamental questions about the universe, including the origins of planetary systems, the distribution of organic molecules, and the potential for life beyond Earth. By investing in the development of these cutting-edge technologies, scientists are laying the groundwork for a new era of discovery that will expand our understanding of the cosmos and our place within it. The study of interstellar objects is not just about understanding these individual objects, but about unlocking the secrets of the wider galaxy and potentially even the universe beyond.
Mars has long fascinated humans as a potential abode for life. The idea of the red planet as Earth's closest neighbor and the possibility that it once harbored life, or still might, has inspired science fiction and real scientific investigation alike. NASA's Mars rovers like Curiosity and Perseverance rovers, central to this quest, have been invaluable tools in unearthing the mysteries of Mars. These robotic geologists were sent on two of the most ambitious missions in space exploration history, to study the Martian environment, understand its history, and assess its potential for hosting life. Over the decades, the discoveries they've made are reshaping our understanding of the red planet, transforming it from a distant celestial object into a world brimming with scientific intrigue. Through a combination of high-resolution imaging, sophisticated chemistry experiments, and relentless perseverance, NASA's rovers have unearthed evidence of Mars's dynamic past, as well as its ability to support life. Join us as we dig deep into how these marvelous machines have revolutionized our view of Mars. Before the age of robotic exploration, our understanding of Mars was largely speculative. Early astronomers, such as Giovanni Schiaparelli, observed what they believed were canali on the Martian surface, suggesting a planet crisscrossed with artificial waterways. This spurred imaginations, leading to the idea that an advanced civilization might reside on Mars. As telescopic observations improved, however, these canals were debunked, and the vision of a thriving Martian society was replaced with one of a cold, barren desert world. Regardless, Mars remained a planetary mystery. Scientists debated whether it once had water or if it could potentially harbor life. The 20th century saw missions like the Mariner flybys, which delivered the first detailed images of Mars's cratered and desolate surface, dimming hopes of any significant life forms. However, the story of Mars was far from over, and the arrival of NASA's Mars rovers opened a new chapter in our understanding of the planet. NASA's twin rovers, Spirit and Opportunity, were launched in 2003 with a primary goal: to search for signs that Mars once had liquid water. For scientists, the presence of water in the past was a key indicator that Mars could have supported life. The two rovers landed on opposite sides of the planet in 2004, embarking on missions that would far outlast their expected lifespans. Spirit landed in Gusev Crater, a site believed to have once been a vast lakebed. Initially, its explorations yielded limited evidence of past water activity. However, after months of travel and several technical issues, Spirit struck geological gold when it examined rocks that appeared to have been altered by water. It found signs of sulfuric acid and magnesium sulfate, suggesting that hydrothermal activity had once taken place there. This discovery led scientists to hypothesize that Mars had not only water, but also environments capable of sustaining life, particularly near volcanic regions like Gusev Crater. On the other hand, Opportunity landed in Meridiani Planum, an area rich in hematite, a mineral that typically forms in water. In one of its earliest discoveries, Opportunity found tiny spherules nicknamed blueberries, which were rich in iron and likely formed in the presence of liquid water. It also found evidence of ancient shorelines, revealing that Meridiani Planum was once a shallow sea or salty body of water. These groundbreaking discoveries altered our view of Mars. It was no longer just a cold and lifeless desert. Mars had a wetter and potentially more habitable past. The implications of this were immense. If liquid water had once existed on Mars, could life have also evolved there? Spirit and Opportunity provided the first compelling evidence that Mars might have once had the right conditions to support microbial life. If Spirit and Opportunity laid the groundwork, NASA's Curiosity rover, launched in 2011, pushed the boundaries of Martian exploration even further. Designed as a mobile laboratory, Curiosity's mission was not only to look for signs of water, but also to assess the planet's potential to support life by studying its climate and geology. Curiosity landed in Gale Crater, an area with a rich geological history. As it climbed the lower slopes of Mount Sharp, the mountain at the center of the crater, it uncovered layers of sedimentary rock that told the story of a once habitable environment. The sediments appeared to have been laid down by ancient lakes that persisted for millions of years, offering a stable, water-rich environment. This was one of the most significant findings in Mars exploration, suggesting that Mars was not only occasionally wet, but had long-lasting bodies of water that could have been home to life. Another major discovery came when Curiosity detected organic molecules in Martian soil. While these molecules are not direct evidence of life, they are considered the building blocks necessary for life to form. The detection of these organic compounds was a tantalizing hint that Mars had the raw materials needed for life, further raising the possibility that life could have once existed on the planet. Curiosity also measured methane in the Martian atmosphere, a gas that, on Earth, is primarily produced by biological processes. While the source of Mars methane remains a mystery, its presence is yet another clue that Mars' past or even present conditions could be conducive to life. Curiosity's discoveries then laid the foundation for the next phase of Martian exploration: the search for direct evidence of ancient life. NASA's Perseverance rover, which landed in Jezero crater in 2021, is equipped with more advanced instruments designed to probe the planet's ancient environments and look for biosignatures, fossilized evidence of past life. Jezero crater is an ancient lakebed that once housed a delta where rivers deposited sediments. This delta is a prime target for the search for life, as deltas on Earth are often rich in microbial life and well-preserved fossils. Perseverance has already found evidence of ancient river channels and lake sediments, further confirming that Mars once had a warm and wet climate capable of sustaining water for long periods. One of Perseverance's key objectives is to collect rock and soil samples that could one day be returned to Earth for more detailed analysis. These samples are expected to contain clues about Mars's geology, climate, and perhaps even past life. The Mars Sample Return mission, currently in development, could bring these samples back to Earth in the 2030s, offering scientists an unprecedented opportunity to study the red planet in the lab. In short, NASA's rovers have not only transformed our understanding of Mars' geology and potential habitability, but have also shed light on its climate and atmosphere. Both Curiosity and Perseverance have been instrumental in measuring atmospheric conditions on Mars, revealing that the planet's atmosphere is much thinner and more dynamic than previously thought. Mars's atmosphere, which is mostly carbon dioxide, is too thin to support liquid water on the surface today. However, data from the rovers suggest that in the distant past, Mars had a thicker atmosphere capable of supporting lakes and rivers. Understanding how Mars lost this atmosphere is a key question in planetary science, as it could offer insights into how planets evolve and lose their habitability. Moreover, measurements of Martian dust storms, temperature fluctuations, and radiation levels have provided crucial information for future human exploration. The thin atmosphere allows for dangerous levels of solar and cosmic radiation to reach the surface, presenting a significant challenge for manned missions to Mars. It doesn't stop there. NASA's rovers have also revealed that Mars is far more geologically active than once thought. Spirit, Opportunity, Curiosity, and Perseverance have all encountered evidence of active erosion, shifting sand dunes, and even seasonal changes in methane concentrations. These findings suggest that Mars is not a completely dead world, but one where geological processes are still occurring, albeit at a slower rate than on Earth. Curiosity's discovery of recurring slope lineae, dark streaks that appear on Martian hillsides during warmer months, raise the possibility that liquid water might still exist on Mars today, albeit in small, seasonal amounts. While this remains a topic of debate, it underscores the fact that Mars continues to surprise us with its dynamic environment. NASA's rovers have fundamentally altered our understanding of Mars, but the story is far from over. The next wave of Mars missions promises to push the boundaries even further, moving from robotic exploration to the potential for human settlement. These future missions aim to uncover the remaining mysteries of Mars's geology, atmosphere, and habitability, while advancing our technology to prepare for human exploration. Let's explore some of the most anticipated upcoming missions and how they are poised to change our relationship with the Red Planet. Number 1. Mars Sample Return Mission. One of the most ambitious and eagerly awaited missions is the Mars Sample Return, a collaboration between NASA and the European Space Agency, also known as the ESA. The goal of the Mars Sample Return is to bring Martian soil and rock samples back to Earth for detailed analysis, providing insights that current Mars rovers and orbiters cannot deliver. The groundwork for the Mars Sample Return mission has already been laid by NASA's Perseverance rover, which is currently collecting samples from the Jezero crater, a site believed to have been home to an ancient lake and delta. These samples are being sealed in specialized tubes and cached at select locations on Mars, where they will be retrieved by future missions. The Mars Sample return mission will consist of several key phases. A fetch rover, developed by ESA, will land on Mars to collect the sample tubes left by Perseverance. These samples will then be transferred to the Mars Ascent Vehicle, a small rocket that will launch the samples into Martian orbit, the first ever rocket launch from another planet. Once the samples are in orbit, they will be intercepted by an Earth return orbiter and safely transported back to Earth. If all goes according to plan, the samples could arrive in the early 2030s, marking a historic milestone in planetary science. On Earth, scientists will study the samples using cutting-edge technology, including techniques that far exceed the capabilities of instruments currently on Mars. This will allow for a more precise analysis of Mars's geology, climate history, and, most excitingly, the search for potential biosignatures of ancient Martian life. Number 2. Human missions to Mars, a new frontier. While robotic missions have provided invaluable data, the ultimate goal for space agencies like NASA, SpaceX, and other international organizations is to send humans to Mars. This would be the most ambitious endeavor in space exploration history, with enormous scientific, technological, and geopolitical implications. NASA's Artemis program is focused on returning humans to the Moon by 2025, but its broader objective is to serve as a stepping stone for human missions to Mars. Through Artemis, NASA plans to develop and refine the technologies and techniques necessary for long-duration space travel and deep space habitats, which are crucial for any future human mission to the Red Planet. The Lunar Gateway, a space station in orbit around the Moon, will be a key part of this effort. It will provide a platform for testing life support systems, radiation protection, and other technologies required for Mars missions. The knowledge gained from establishing a sustained human presence on the Moon will directly inform the planning for Mars missions, including the construction of habitats, the development of energy sources, and the extraction of local resources like water ice. Elon Musk's SpaceX has positioned itself as a leader in the race to Mars with the ambitious goal of establishing a human colony on the planet. Central to this vision is the Starship spacecraft, which is designed to transport humans and cargo to Mars. Starship is still in the development phase, but SpaceX has already conducted numerous test flights. When operational, Starship will be capable of carrying up to 100 passengers and large amounts of cargo, making it the most advanced spacecraft ever built for deep space missions. SpaceX plans to send unmanned Starship missions to Mars in the coming years to test the technology and deliver essential supplies, with the goal of sending the first human missions by the early 2030s. Musk's vision doesn't stop at exploration. He envisions the creation of a self-sustaining human colony on Mars. To achieve this, SpaceX will need to solve several key challenges, including developing technologies for producing fuel, water, and oxygen on Mars, a concept known as in situ resource utilization. Establishing a permanent human presence on Mars will also require the construction of habitats that can withstand the planet's harsh climate, including extreme cold, high radiation levels, and dust storms. At that time, life support systems are a critical component. Astronauts will need to survive for extended periods of time in the harsh Martian environment where the atmosphere is primarily carbon dioxide and temperatures can drop as low as 80 degrees Fahrenheit. NASA is developing systems that can generate oxygen from the Martian atmosphere, a key innovation for sustaining human life on the planet. The Perseverance rover, which landed on Mars in 2021, carried an instrument called MOXIE for Mars Oxygen In Situ Resource Utilization Experiment to demonstrate the production of oxygen from the planet's atmosphere. Successful technologies like MOXIE will be essential for long-term human habitation. Radiation is another major challenge for human missions to Mars. Unlike Earth, Mars does not have a strong magnetic field to protect it from harmful cosmic rays and solar radiation. Astronauts traveling to and living on Mars will need protection from this radiation. Engineers are exploring solutions such as radiation-hardened habitats, advanced shielding materials, and possibly underground living quarters to mitigate the risk. Otherwise, the journey to Mars itself is fraught with challenges. The first and most obvious is the distance. Mars is an average of 140 million miles away from Earth, depending on the planetary alignment. This means that a one-way trip to Mars would take about 6 to 9 months. During this time, astronauts would be isolated from Earth, enduring the psychological and physical stresses of long-duration spaceflight. Communication delays would further compound these difficulties, with messages taking anywhere from 4 to 24 minutes to travel between Earth and Mars. One of the biggest hurdles will be ensuring that astronauts have enough food, water, and supplies for the entire mission. NASA and other organizations are researching ways to grow food on Mars, such as hydroponic farming, to reduce the need for resupply missions. Additionally, extracting water from the Martian soil, known as regolith, will be essential for both drinking water and the production of fuel. Landing on Mars is another monumental challenge. Mars has a thin atmosphere, which makes it difficult to slow down a spacecraft using traditional parachutes and rockets. NASA's Perseverance rover used a combination of parachutes, rockets, and a sky crane system to land, but scaling this up for a crewed mission will require further innovation. Fortunately, with technology advancing at an unprecedented rate, the next few decades could see humans setting foot on the Martian surface. At that time, these missions would represent a major milestone in human exploration and a paradigm shift in our understanding of what it means to be a spacefaring species. The scientific discoveries made on Mars could reshape our understanding of planetary evolution, climate, and the possibility of life beyond Earth. But the implications extend far beyond science. The successful colonization of Mars would signify that humanity is no longer confined to Earth. It would mark the beginning of a new era in which humans could explore, live, and thrive on other planets. This could open up opportunities for further exploration of the solar system and beyond. In the long term, it could even serve as a safeguard for the survival of humanity, offering a second home in the event of catastrophic events on Earth. Number 3. Mars Ice Mapper, unlocking Mars water resources. Water is essential for human exploration and settlement on Mars, both as a vital resource for astronauts and as a potential source of fuel via water electrolysis to produce hydrogen and oxygen. NASA, in partnership with international space agencies, is developing the Mars Ice Mapper mission to search for subsurface water ice across the planet. Scheduled for launch in the late 2020s, the Mars Ice Mapper will carry a synthetic aperture radar instrument designed to detect water ice deposits up to several meters below the surface. These water ice reserves could be used to support human missions by providing drinking water, growing food, and producing fuel, reducing the need to transport these resources from Earth. The data from the Mars Ice Mapper will also be crucial for identifying the best landing sites for future human missions, as access to water will be a primary consideration for establishing long-term human habitats. While NASA and SpaceX are leading the charge, other nations are also planning future Mars missions, contributing to a global effort to explore the planet. China's space program has made significant strides in recent years, including the successful landing of the Tianwen-1 rover in 2021. China has plans for a Mars sample return mission of its own, which could potentially launch in the 2030s, following in the footsteps of NASA's Mars sample return. Additionally, China has expressed interest in sending humans to Mars, with long-term plans to establish a human settlement by the middle of the century. Elsewhere, Russia has a long history in space exploration and is also eyeing future Mars missions. In partnership with the European Space Agency, Russia is working on the ExoMars program, which aims to explore the Martian surface and search for signs of past or present life. While the ExoMars rover, Rosalind Franklin, has faced delays, it is still expected to play a crucial role in future Mars exploration. India, which successfully placed its Mangalyaan orbiter around Mars in 2014, is planning a follow-up mission called Mangalyaan 2. This mission will likely include a more advanced orbiter or even a lander to continue studying Mars's surface and atmosphere. Other countries, such as the United Arab Emirates, or UAE, which launched the Hope Mars mission, are also increasing their investment in Martian exploration, signaling a growing international interest in the red planet. In addition, advancing technology is crucial to the success of future Mars missions, particularly in overcoming the challenges of transportation, sustainability, and survival on Mars. One of the key hurdles in human Mars exploration is the long duration of the trip, up to 9 months with current propulsion technologies. To shorten this travel time and reduce risks, NASA and other space agencies are exploring the potential of nuclear propulsion. Nuclear thermal propulsion and nuclear electric propulsion could significantly reduce travel time to Mars, making missions safer and more efficient. Besides, robotics and AI will play a vital role in future Mars missions, particularly in the construction of habitats and infrastructure. Autonomous robots could be sent ahead of human missions to build landing pads, habitats, and resource extraction facilities, reducing the workload for astronauts and increasing the likelihood of mission success. AI will also enhance navigation, scientific analysis, and communication during deep space missions, allowing for more efficient decision-making and reducing delays caused by the time it takes for signals to travel between Earth and Mars. On the other hand, we all know that one of the biggest challenges facing human missions to Mars is the planet's lack of a protective magnetic field and thick atmosphere, which means astronauts will be exposed to high levels of cosmic radiation. Researchers are developing advanced radiation shielding materials and technologies, such as underground habitats or regolith-based shelters, to protect future Mars explorers. Additionally, life support systems capable of recycling air, water, and waste are being refined to ensure that astronauts can survive and thrive during long-duration stays on Mars. After all, the future of Mars exploration is a blend of robotic missions, technological innovation, and the bold ambition to send humans to the red planet. From the Mars sample return mission to the dreams of SpaceX's Starship colonizing Mars, these missions will transform our understanding of Mars and lay the groundwork for humanity's expansion beyond Earth. As we look to the coming decades, Mars will not just be a distant red dot in the night sky. It will become a second home, a new frontier where humans will continue their quest for knowledge, discovery, and survival. The race to Mars is no longer a distant vision. It's a rapidly approaching reality. And of course, the red planet is not the only choice. Beyond Mars, there is a lot of intriguing places to search for life in the solar system. One of which is Europa, one of Jupiter's largest moons. Europa is covered in a thick layer of ice, but beneath that ice lies a vast, global ocean that could be twice the volume of all Earth's oceans combined. This hidden ocean, kept warm by tidal heating from Jupiter's immense gravitational pull, has long fascinated scientists as a potential habitat for life. Human missions to Europa would be extremely challenging due to the moon's distance from Earth and the harsh conditions of its surface, which is bombarded by intense radiation from Jupiter. However, future missions could involve astronauts landing on Europa and drilling through its icy shell to explore the ocean below. Submersible probes could be sent into the waters to search for signs of life, perhaps microbial organisms similar to those found in Earth's deep oceans near hydrothermal vents. The presence of water is a key ingredient for life as we know it, and Europa's ocean, rich in potential energy sources, could offer an environment where life might thrive. If we were to discover life on Europa, it would suggest that life can arise in environments vastly different from Earth's, expanding our understanding of habitability and the potential for life in the universe. Like Europa, Saturn's moon Enceladus also harbors a subsurface ocean beneath its icy crust. What makes Enceladus particularly intriguing is its geysers, plumes of water vapor, organic molecules, and ice particles that shoot out from cracks near its south pole. These geysers provide a direct window into the moon's subsurface ocean, allowing scientists to study its composition without having to drill through the ice. Enceladus's geysers have already been studied by the Cassini spacecraft, which detected organic molecules, water vapor, and evidence of hydrothermal activity. This combination of factors, water, heat, and organic compounds, makes Enceladus one of the most promising places to search for life in the solar system. Future human missions to Enceladus could involve landing near these geysers to study the material being ejected into space. Astronauts could collect samples directly from the plumes, searching for signs of microbial life or other biological processes. If life exists in Enceladus Ocean, it could be similar to the extremophiles that thrive in Earth's deep-sea hydrothermal vents, which rely on chemical energy rather than sunlight. Saturn's largest moon, Titan, is another intriguing target in the search for life. Unlike Europa and Enceladus, Titan does not have a subsurface ocean of liquid water. Instead, it has lakes and rivers of liquid methane and ethane on its surface. Titan's thick atmosphere, composed mostly of nitrogen, is similar to Earth's early atmosphere, and its surface features complex organic chemistry that could potentially give rise to life. While life on Titan would likely be very different from life as we know it, perhaps methane-based rather than water-based, the moon's unique environment offers a fascinating opportunity to explore alternative biochemistries. The search for life on Titan focuses on two main environments, the surface and a hypothesized subsurface ocean. While Titan's surface is cold and harsh, it offers an environment rich in organic molecules, which are the building blocks of life. Complex organic molecules, including hydrocarbons, nitriles, and amino acids, have been detected in Titan's atmosphere and on its surface, providing a chemical laboratory for the potential development of life. The methane and ethane lakes are of particular interest because they offer a stable liquid environment where exotic forms of life might exist using liquid methane instead of water as a solvent. Beneath Titan's icy crust, scientists suspect there may be a vast subsurface ocean of liquid water mixed with ammonia. This ocean, kept warm by tidal forces from Saturn's gravity, could be a more familiar environment for life as we know it. If this ocean exists, it might harbor microbial life similar to Earth's deep-sea organisms that thrive near hydrothermal vents. NASA's upcoming Dragonfly mission, set to launch in the mid-2020s, will take a major step toward exploring Titan's potential for life. This rotorcraft will fly across Titan's diverse surface, studying its atmosphere, surface chemistry, and geology in unprecedented detail. By analyzing the moon's complex organic chemistry, Dragonfly could uncover evidence of prebiotic conditions or even signs of life. Elsewhere, although Venus is often thought of as Earth's evil twin due to its scorching surface temperatures and thick, toxic atmosphere, recent studies have suggested that life could potentially exist in the planet's upper atmosphere. While the surface of Venus is far too hostile for life, with temperatures exceeding 450 degrees or 850 degrees, the atmosphere 50 kilometers above the surface has more temperate conditions, with temperatures and pressures similar to those on Earth. In 2020, scientists detected the presence of phosphine gas in Venus's atmosphere, a potential biomarker for life. While the discovery is still debated and requires further investigation, it has renewed interest in Venus as a possible location for microbial life. Future human missions to Venus could involve floating cities or airships in the planet's upper atmosphere, where astronauts could study the chemical composition of the clouds and search for signs of life. While Venus is not the most obvious candidate for life, it serves as a reminder that life could exist in unexpected places, even on planets that seem inhospitable at first glance. While the gas giants Uranus and Neptune are unlikely to harbor life due to their extreme atmospheres, composed largely of hydrogen, helium, and methane, with crushing pressures and frigid temperatures, their moons present more promising environments in the search for life. Both planetary systems host a variety of moons, some of which display intriguing characteristics that could support microbial life or prebiotic conditions. Uranus has 27 known moons, with several of its largest, Titania, Oberon, Umbriel, Ariel, and Miranda, showing signs of geological activity and potential subsurface oceans. Titania and Oberon, in particular, are believed to possess water ice beneath their surfaces. If internal heating, perhaps caused by tidal forces from Uranus, is enough to keep these oceans from freezing solid, they could provide environments where life might thrive, similar to the subsurface oceans hypothesized for other icy moons in the solar system. Neptune's largest moon, Triton, is one of the most compelling candidates for life in the outer solar system. Triton is a captured Kuiper Belt object, with a retrograde orbit and an icy surface marked by active geysers that spew nitrogen gas. These geysers indicate internal heating, likely caused by tidal forces exerted by Neptune. Beneath Triton's icy crust, there could be a subsurface ocean of liquid water mixed with ammonia, which would act as an antifreeze. This subsurface ocean could create conditions suitable for life, protected from the harsh conditions of space. Of course, the search for life on other planets and moons will not be easy. The distances involved are vast, the environments are harsh, and the technological challenges are immense. However, advances in propulsion technology, robotics, and life support systems will make future human missions to these distant worlds possible. The search for life in the solar system is not just about finding new forms of biology. It's about understanding the nature of life itself and our place in the vast cosmos. And one day, it would answer the age-old question of whether we are alone in the universe and open up a new era of exploration focused on understanding how life arises and evolves in different environments. A black hole is one of the most fascinating of all cosmic phenomena. Essentially, black holes are locations in space that completely overturn our intuition of how space and time behave. In movies, they are often depicted as the ultimate danger, ravenous monsters that will reach out and grab any unwitting spaceship that falls into their gravitational field. Even weirder, their interior is cloaked in mystery. Scientists using Einstein's theory of general relativity tell us that the center of a black hole is a singularity, a place where an amount of mass equivalent to at least 5 times that of our Sun is compressed into a spot with zero volume. So, what is the reality of black holes, and is there any truth to that singularity idea? All this and more will be discussed in today's episode. The idea that black holes exist has been around for longer than most people realize, since the late 18th century, when John Michell first suggested them. He noted that if you took something like our Sun, with a known mass and volume, and simply created a bigger version of it, with more mass occupying more volume at the same density, you'd eventually reach a critical situation. At some point, with more mass gathered together in one region of space, you'd find that the escape velocity from the surface, or the speed at which you needed to move to escape from the object's gravitational pull, would exceed the speed of light, 300,000 km/s. From outside of this object, you wouldn't be able to see anything at all, as not only could light not escape from it, but no particles or signals of any type. Anything that happens within the interior of that surface, where the escape velocity is greater than or equal to the speed of light, can never get out. With that, the idea of a black hole was born. And a little over 100 years later, when Einstein came up with the general theory of relativity as our new theory of gravitation, the idea of a black hole became even more compelling and robust. According to Einstein, it isn't that objects have mass and massive objects attract one another through an invisible force. That conception of gravity is Newtonian and cannot explain a whole host of observational phenomena, from the gravitational bending of light to the orbit of Mercury, to the presence of gravitational waves, and much more. Instead, Einstein's revolutionary new way to view the universe asserted that matter and energy alter the curvature of space-time and affect its evolution, and that this curved and evolving space-time tells matter and energy how to move within it. If you have a point-like mass in your universe, that creates the Schwarzschild space-time, the space-time that describes a non-rotating black hole. Any massive particle that you place down in that space-time will experience the space-time curvature induced by that black hole. If that particle is outside the black hole's event horizon, then it could still escape from the black hole's gravitational pull if it were moving fast enough. However, if that particle were placed inside the black hole's event horizon, then it could never escape, and must instead wind up at the central point, the singularity, after a finite and calculable amount of time. What was remarkable about black holes in general relativity is how easy they were to produce theoretically, as well as how difficult they were to avoid. One of the earliest results that Einstein was able to show is that if you began with flat, static, unchanging spacetime, and you put down a set of stationary, pressureless masses within it, i.e., dust particles, and you allowed those masses particles to evolve, then they would all gravitate. And in very short order, you'd inevitably form a non-rotating black hole, event horizon and all. It's as though you have to have something else at play to avoid forming a black hole from an initial distribution of masses. Normally, that something else is some type of pressure that holds matter up against further collapse. Atoms have a pressure from the electron clouds around them. Stars have a pressure from the radiation generated through nuclear fusion. But for massive enough stars, or massive enough collections of matter in general, it's possible to overcome that pressure and create a black hole after all. This was famously shown in the mid-20th century by Roger Penrose, who won a Nobel Prize for his efforts to show how black holes can realistically form within our universe. And while black holes are the darlings of science and science fiction, the fact that the ironclad evidence for black holes was a long time coming. The first suspected black hole was Cygnus X1, a system involving what was believed to be a black hole as a member of an X-ray binary system. Famously, in 1974, leading black hole theorists Stephen Hawking and Kip Thorne playfully made a bet, Hawking betting against its confirmation as a black hole and Thorne for it. The evidence was a long time coming. Finally, in 1990, Cygnus X1 was confirmed as a black hole and Thorne won the bet. The 1990s transformed into a boon for black hole discoveries. It soon became clear that several types of black holes exist, or must exist. The most abundant type must be stellar black holes, like Cygnus X1, that form from the deaths of massive stars. These stellar black holes must exist in the millions even in our Milky Way galaxy, but they are very hard to find. Detecting them involves favorable circumstances and their involvement with other luminous objects, as in a binary system. We still know of only a couple dozen in our own galaxy. However, soon commenced an explosion of discoveries of another abundant type, supermassive black holes. These form at the centers of most galaxies, and they range from millions to billions of times the mass of the Sun. The Hubble Space Telescope uncovered evidence of countless supermassive black holes, and we know that one, Sagittarius A, exists in the center of our own Milky Way. Based on their understanding of the early cosmos, Astronomers also believe that primordial black holes emerged soon after the Big Bang, some 13.8 billion years ago. These are tiny black holes that may have been the size of an atom. The smallest primordial black holes have doubtless evaporated, but larger ones may still exist. And in recent times, evidence has emerged for a fourth class, so-called intermediate mass black holes. These objects range from hundreds to hundreds of thousands of solar masses, and evidence for a small number of these objects is emerging. They may form in unusual cosmic arrays, such as environments crowded with stars, from mergers of stellar black holes, or from some other phenomena. Early on, the idea of a black hole captured the imaginations of writers. As regions of space with such strong gravity that nothing can escape, not even light, they are irresistible as objects of speculation. What would exist within a black hole? What would happen if a spacecraft approached a black hole? And perhaps the ultimate question, could a person survive traveling into a black hole? To solve these questions, let's start with the easiest, approaching a black hole. Far outside of a black hole, the gravity they exert is really quite ordinary. Replace the sun with a black hole with the same mass, and the Earth would continue its stately march through the solar system, circling the black hole every 365.25 days. Admittedly, the Earth would be dark and begin to freeze, but gravitationally speaking, there would be no change. When one gets closer to the black hole, however, the story becomes different. What does closer mean? When talking about black holes, there are a couple of radii that are noteworthy. The first, as told, is the singularity. General relativity says that all of the mass of the black hole has been crushed by gravity down to literally zero size. So, it might be sensible to say that the radius of a black hole is zero. Another important feature is a sphere called the event horizon. The event horizon is defined by the behavior of light. Light, like mass, is affected by gravity. In the same way that it takes energy to lift a rocket from the surface of the Earth into space, it takes energy for light to leave a heavy object. The stronger the gravity, the more energy it takes for light to escape. As one gets closer and closer to the center of a black hole, gravity becomes stronger and stronger. There is a radius at which an object traveling at the fastest speed possible, the speed of light, can no longer escape the black hole. The size of the event horizon depends on the mass of the black hole, but other important parameters include whether it is rotating and whether it has electric charge. However, for the simplest possible black hole, one that is both uncharged and not rotating, the radius of the event horizon is called the Schwarzschild radius, named after the German physicist and astronomer Karl Schwarzschild. For distances closer to the center of the black hole than the Schwarzschild radius, nothing can escape, not even light. Outside it, objects can escape, at least in principle. For an object with the mass of the Sun, the Schwarzschild radius is approximately 3 kilometers. In contrast, the radius of the Sun is about 700,000 kilometers, or 435,000 miles. The Schwarzschild radius of the Earth is just shy of a centimeter. At distances of about 2.5 times the Schwarzschild radius, objects can orbit the black hole. From about 2.5 to 1.5 times the Schwarzschild radius, orbiting is difficult and unstable, requiring enormous effort to sustain the orbit. At about 1.5 times the radius of the event horizon lies the photon sphere. At this distance, the black hole bends space so much that photons of light actually orbit the black hole. If you were at this distance from a black hole, the light from the back of your head would circle the hole and hit you in the face. You wouldn't need a mirror to see if you combed your hair properly. Getting closer to the black hole, things get even stranger. A person far from the black hole would see objects approach the event horizon moving slower and slower and eventually fade from view. However, as a person approaches the event horizon, nothing much changes, though the view one has of the surrounding sky becomes heavily distorted by the gravitational field of the black hole. Once a person passes the event horizon, That's the point of no return. Once there, you can never leave. And here's the interesting thing. Because nothing can leave the event horizon, we have no data about what occurs inside. Our understanding of the nature of space and time inside a black hole is entirely theoretical, and these ideas may or may not be right. However, according to theory, space and time become reversed inside the event horizon. As you move toward the center of the black hole, you are moving in time, not space. This is a crazy idea, but it might be true. It's when one approaches the center of the black hole that our ignorance of measurement is joined by an ignorance of theory. The theory breaks down. It is common to hear that the center of a black hole is a singularity, a theoretical place where the mass of the hole is compressed into zero size. But this isn't what a singularity really means. A singularity is a place where the theory breaks down. If one takes general relativity seriously, the zero-size option is real. But that would also mean a place of infinite density. And what all of this really means is that our theory no longer works. Among practicing scientists, the consensus is that the singularity means that general relativity fails. As such, what we need is a new theory of gravity, what scientists call quantum gravity. And here is an unsettling truth. Scientists don't really know what that theory looks like. Regardless, they have some ideas. Some physicists propose that instead of a classical singularity, the center of a black hole could contain a quantum object, a point where quantum effects prevent the infinite collapse predicted by general relativity. This theory ties into ongoing attempts to unify general relativity and quantum mechanics into a theory of quantum gravity. In this scenario, the singularity is replaced by a region where the forces of quantum mechanics balance the gravitational pull, preventing the complete destruction of space-time. This is purely hypothetical at this stage, but such ideas are gaining traction as researchers push forward in understanding quantum gravity. Another theoretical model for the interior of a black hole is the Planck star, proposed in 2014 by physicists Carlo Rovelli and Francesca Vidotto. In this model, black holes do not collapse into singularities. Instead, they form extremely dense Planck stars, where quantum effects of gravity create immense pressure, stopping the collapse before a singularity can form. In the Planck star model, as the black hole evaporates via Hawking radiation, the star inside eventually releases the information it has stored, avoiding the loss of information paradox. One of the more speculative and exciting ideas is that black holes might act as portals to other regions of space-time, or even to alternate universes. This idea stems from solutions to Einstein's equations that allow for the existence of wormholes, tunnels through space-time that could connect distant parts of the universe. While wormholes are mathematically possible, they are highly speculative, and no observational evidence has yet confirmed their existence. Nonetheless, if black holes were connected to wormholes, the singularity at the center might be replaced by a pathway to another part of the cosmos, or perhaps to a parallel universe. Ultimately, the mystery of what lies inside a black hole may remain unsolved for the foreseeable future. The very nature of black holes prevents us from directly observing their interiors, and current scientific tools and theories are limited in explaining what happens beyond the event horizon. However, black holes also serve as laboratories for exploring some of the most fundamental questions about the universe, from the nature of time and space to the unification of quantum mechanics and gravity. In some ways, asking what's inside a black hole is as much a philosophical question as it is a scientific one. Are we, as finite beings, capable of ever truly comprehending the infinite forces at work within these cosmic monsters? Or will black holes remain eternal enigmas, hinting at the vast unknowns that lie beyond the limits of human understanding? In short, as technology advances, particularly with instruments like the James Webb Space Telescope and other cutting-edge observatories, we may one day unlock further secrets about these cosmic giants. Perhaps we'll find that the true nature of a black hole is something entirely beyond our current comprehension, a key to understanding not only the universe, but the very fabric of reality itself. Another secret: when something falls into a black hole, where does it go? And will it ever come back out again? According to Einstein's general relativity, those answers are simple. As soon as anything physical, matter, antimatter, radiation, etc., crosses over the event horizon, it's gone. It can add things like mass, electric charge, and angular momentum to the black hole, but little else. It goes swiftly toward and eventually into the central singularity and will never escape again. But our universe isn't governed by general relativity alone, but also by quantum physics. According to our best understanding of quantum reality, there's much more that needs to be considered. Not only are there other quantum properties inherent to the raw ingredients that go into making a black hole: baryon number, lepton number, color charge, spin, lepton family number, weak isospin and hypercharge, etc. But the fabric of space-time itself, which contains the black hole, is quantum in nature. Because of those quantum properties, black holes do not remain static, but rather evaporate over time, emitting Hawking radiation, and perhaps even more, in the process. When black holes do evaporate, then, what happens to the information that went into creating them? Is it conserved? Is it destroyed? Is it encoded in the outgoing radiation? And if so, how? These questions are at the heart of perhaps the greatest paradox of all, the black hole information paradox. Here's both what we know and what we still need to find out. When a physicist talks about information, they don't necessarily mean what we conventionally think of as information, a string of letters, numbers, symbols, or anything else that can be encoded with bits like zeros or ones. Conventionally, this is often described as the number of yes-no questions that must be answered to fully specify the properties of your physical system, although even that description has limitations. These are all certainly examples of information, but those examples don't encompass all the various types of information that exist. Information can also include signals that enforce causality, quantum states, like qubits instead of bits, for individual entities, entangled quantum states between multiple entities, or any measure of the physical quantity known as entropy. That last one is tricky, because entropy, an inherently thermodynamical quantity, is very often misunderstood. You'll often hear statements like, entropy is a measure of disorder, or entropy always increases for any system. And while those things are kind of true, it's possible to make very ordered high-entropy systems and to decrease a system's entropy through the input of an external energy source. As an alternative, consider this. What entropy actually measures is the number of possible arrangements of the fully quantum state of your system. A classic example is to consider two systems. A room with a divider in it, where one side of the room is filled with hot gas and the other side is filled with cold gas. And that same room, with the same gases, except the divider is open and both sides of the room have reached the same temperature. Both systems have the same number of particles, the same total energy in them, but wildly different entropies from one another. The second system has a much greater amount of entropy, as there are many different ways to distribute energy among all of the particles in your system to achieve the desired configuration than there are for the first system. The number of possible arrangements of the fully quantum state of your full system is much greater for the second system than the first. Because there is a greater number of possible arrangements, you have to provide a greater amount of information, and therefore answer a greater number of yes-no questions, to fully describe the system with a greater amount of entropy. Information and entropy aren't identical, but they are proportional. A greater entropy to your system means it requires more information to fully describe it. If you take a book and burn it, the book's information doesn't get lost or destroyed, but merely scrambled. In principle, although maybe not in practice just yet, you could trace each and every particle of paper and ink that went into the fire, determine where they went, and from the ash, soot, chemicals, and invisible gases they produced, keep track of every character on every page in that book. In principle, you could look at that final system of the completely burned book and reconstruct the complete information that was in the book before you burned it. You can do this with the remnants of a shattered glass, reconstructing what the original unbroken structure looked like. You can do this with a scrambled and cooked egg, reconstructing what the uncooked, unscrambled egg was like. As long as the fundamental particles that the original system was made out of were preserved, no matter what interactions they underwent in the meanwhile, that original information about the initial state of the system would be preserved as well. But with black holes, that absolutely isn't the case any longer. In general relativity, black holes don't have any memory about the types of particles, or the properties of those particles, that went into creating or growing the black hole. The only measurable properties a black hole can possess are mass, electric charge, and angular momentum. In the early 1970s, this puzzle was considered by physicist Jacob Bekenstein, who recognized why this was such a problem. Whatever particles go into forming a black hole have their own properties, configuration, and amount of entropy and information encoded within them. According to the second law of thermodynamics, entropy can never decrease for a closed system. It can only increase or remain the same unless some external source of energy is inputted to decrease that entropy. And even then, the total entropy of the original system plus the external source, where the external source is where that inputted energy comes from, will continue to increase. But in pure general relativity, black holes have zero entropy, and that definition simply won't work. From the perspective of an external observer, it's quantum particles that go into the creation of a black hole, and as the black hole gets created and grows, the surface area of its event horizon increases. As the mass goes up, the surface area goes up, and as more particles pour in, the entropy must rise as well. It was Bekenstein who first recognized that the information encoded by the infalling particles would, from an external observer's perspective, appear to get smeared out over the surface of the event horizon, enabling a definition of entropy that was proportional to a black hole's event horizon's surface area. Today, this is known as the Bekenstein-Hawking entropy, the entropy of a black hole. This definition was very exciting, but the notion that we had made sense of the universe, of entropy, information, and black holes was extremely short-lived. In 1974, just 2 years after Bekenstein's earliest work on the topic, Stephen Hawking came along and not only had a spectacular realization, but performed a tremendous calculation to go with it. His realization was that the standard way of performing quantum field theory calculations made an assumption that space would, on tiny quantum scales, be treated as though it were flat, unaffected by the general relativistic curvature of space. However, in the vicinity of a black hole, this wasn't just a bad approximation, it was a worse approximation than it would be under any other conditions that occurred within our physical universe. Instead, Hawking recognized the calculation needed to be done in a background of curved space, where the background spatial curvature was given by Einstein's equations and the properties of the black hole in question. Hawking calculated the simplest case, for a black hole with mass only without electric charge or angular momentum, in 1974, and recognized that the state of the quantum vacuum, or empty space itself, was fundamentally different in curved space near the black hole's event horizon than the state of the quantum vacuum far away from the black hole, where space is flat. That calculation revealed that black holes don't simply exist stably in this curved space, but that the differences in the vacuum near and far away from the event horizon lead to a continuous emission of blackbody radiation. now known as Hawking radiation. This radiation should have a blackbody spectrum, be made almost exclusively of massless photons, not one member of particle-antiparticle pairs, should radiate at a very low temperature that's inversely proportional to the mass of the black hole, and should evaporate in a time that's proportional to the mass of the black hole cubed. This is remarkable and is a purely quantum effect that we're now realizing may apply to systems other than black holes as well. However, it raised a new, troubling issue. If the radiation that comes out of a black hole as it evaporates, this Hawking radiation, is purely blackbody in nature, it should have no preference for matter over antimatter, baryons over antibaryons, leptons over antileptons, one lepton family over another, or any other metric needed to answer a yes-no question regarding the initial quantum state of the matter that went into creating the black hole in the first place. For the first time, it seems that we've encountered a physical system where knowing and measuring all of the information about its final state doesn't, even in principle, allow you to reconstruct the initial state. So where, then, does the information go? That's the puzzle. We think that information shouldn't be able to be destroyed, but if the black hole is evaporating into pure blackbody radiation, then all of that information that went into making the black hole has somehow disappeared. It's possible, of course, that what we think we know about information, entropy, and thermodynamics is not correct, and that black holes really are information-destroying entities. It's also possible that even if we don't presently understand the mechanism by which it occurred, that there's some relationship between, from the perspective of an observer outside the event horizon, the information encoded on the surface of a black hole and the information encoded in the outgoing radiation. And if we're truly keeping an open mind, it's possible that something more fundamentally complex is occurring, that the information that goes into making and growing a black hole gets mixed up somehow in the interior of a black hole, and then is encoded in some non-trivial fashion in the radiation when the black hole itself evaporates. The truth is, despite many declarations over the years that the black hole information paradox has been resolved, that nobody knows. Nobody knows whether the information is preserved, whether it's destroyed or erased, and whether it depends on what occurs in a black hole's interior or whether it can be completely described from an outside observer's perspective. We have mathematical correspondences between what happens on the inside and the outside of a black hole, including an underappreciated fact that takes us beyond the semi-classical approximation used by Hawking, that when radiation comes out of a black hole, it should maintain a quantum mechanical entangled link to the black hole's interior. We have devised methods that allow us to map the entropy of a black hole's interior onto the outgoing radiation that arises due to the Hawking mechanism, which suggests, but does not prove, that we may be approaching a mechanism for understanding how the information that went into creating a black hole gets encoded back into the universe outside of the black hole's event horizon. Unfortunately, we don't know how to calculate individual bits of information using any of these methods. We only know how to calculate overall amounts of information as though we're putting them on a scale, seeing whether they balance or not. That's an important step, but it isn't enough to resolve this paradox. Certainly, there are other ideas that are playing a major role. String-inspired ideas, as well as the notion of a firewall appearing partway through the evaporation process, are considered by many working on the paradox. Others suggest that there are correlations between every quantum of radiation emitted in the Hawking process, similar to entanglement, and that the full suite of those correlations must be understood in order to resolve the paradox. But others have suggested altering the black hole's internal and external geometries over the course of the emission of Hawking radiation to attempt to preserve information, while others appeal to whatever strong quantum effects must be present at the interface of quantum physics and relativity. becoming important in the final stages of black hole evaporation. However, we still do not understand the most important aspects of the paradox: where the information from the particles that create the black hole goes, and how that information, assuming it does get out into the universe again, actually gets encoded into the outgoing radiation that results when black holes evaporate. Despite whatever claims you may have heard, make no mistake, the black hole information paradox is still an unresolved paradox, and although it's still an active area of research, no one can be sure what the solution will ultimately be or what method will eventually lead us to it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Every once in a while, a stellar cataclysm occurs in our universe, bringing the life of a star to an end. The most common type of cataclysm is a core collapse supernova, where a massive star's interior implodes, leading to a runaway fusion reaction and a tremendous explosion, where the energy emitted by the star can briefly shine billions of times brighter than a typical star. And yet, it's the rarer types of stellar cataclysms: superluminous supernovae, hypernovae, tidal disruptions events, and even more exotic explosions that can shine brighter than anything else we have observed.
One star glowing as brightly as a billion, well, it's something called a supernova explosion. It's the death of a massive star.
Notably, such a spectacle of a lifetime is coming closer than ever. You must have guessed it. We're talking about the star Betelgeuse, which someday soon may offer up the greatest fireworks display the human race has ever seen. Located a mere 642 light-years away, Betelgeuse is a bright red pulsating point of light in the constellation Orion. A member of a class of titanic stars known as red supergiants, Betelgeuse is one of the largest stars we know of, with a girth that is truly mind-blowing. If we were to swap it out for the Sun, its outer edge would consume the inner planets, including Earth, and reach beyond the orbit of Mars. In recent years, astronomers noticed that Betelgeuse had begun acting oddly. In a matter of days, it had it visibly and drastically dimmed by some 60%, an episode dubbed the Great Dimming Event. At the same time, its shape had changed from a sphere to something resembling a deflated football. However, just in recent weeks, the star has at times shown more than 50% brighter than normal, drawing renewed attention from the whole world. The sudden fluctuations led researchers to believe that Betelgeuse may have entered a stellar death spiral and that a massive explosion, known as a supernova, was imminent. The situation is so intense that even the physicist Brian Cox also has broken his silence to warn us about a blast so bright it would outshine even the moon in our night sky.
If we take the lines away, the most interesting star, I think, the star that could be shocking in our sky is this one, Betelgeuse or Betelgeuse. It's a red giant star. If you put it where the Sun is, it would extend out to the orbit of Jupiter. It's enormous. It's very unstable. It's about to explode.
Join us as we dig deep into how Betelgeuse will explosively end its life in a supernova. Right now, Betelgeuse is absolutely enormous, irregularly shaped, and with an uneven surface temperature. It's more than 2,000 degrees C cooler than our Sun, but also much larger, at approximately 900 times our Sun's radius, and occupying some 700,000 times our Sun's volume. If you were to replace our Sun with Betelgeuse, it would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and even Jupiter. But there are also enormous extended emissions around Betelgeuse from material that's been blown off over the past few dozen millennia. matter and gas that extends out farther than Neptune's orbit around our Sun. Over time, as the inevitable supernova approaches, Betelgeuse will shed more mass, continue to expand, dim, and brighten chaotically, and will burn progressively heavier elements in its core. Even when it transitions from carbon to neon to oxygen to silicon fusion, we won't have any directly observable signatures of those events. The rate of the core's fusion and energy output will change, but our understanding of how that affects the star's photosphere and chromosphere, the parts that we can observe, is too poor for us to extract concrete predictions about. The energy spectrum of the neutrinos produced in the core, the one observable we know will change, is irrelevant as the neutrino flux is far too low to be detectable from hundreds of light years away. But at some critical moment in the star's evolutionary process, the inner core's silicon burning will reach completion, and the radiation pressure deep inside Betelgeuse will plummet. As this pressure was the only thing holding the star up against gravitational collapse, the inner core, composed of elements like iron, cobalt, and nickel, now begins to implode. It's difficult to imagine the scale of this. An object totaling about 20 solar masses spread out over the volume of Jupiter's orbit, whose inner core is comparable to, and more massive than, the size of the Sun, suddenly begins to rapidly collapse. As large as the gravitational force was pulling everything in on itself, it was counterbalanced by the radiation pressure coming from nuclear fusion in the interior. Now, that fusion, and that outward pressure, is suddenly gone, and collapse proceeds uninhibited. The innermost atomic nuclei, a dense collection of iron, nickel, cobalt, and other similar elements, get forcefully scrunched together, where they fuse into an enormous ball of neutrons. The layers atop them also collapse, but rebound against the dense protoneutron star in the core, which triggers an incredible burst of nuclear fusion. As the layers pile up, they rebound, creating waves of fusion, radiation, and pressure that cascade through the star. These fusion reactions take place over a timescale of approximately 10 seconds, and the overwhelming majority of the energy is carried away in the form of neutrinos, which hardly ever interact with matter. The remaining energy-carrying particles, including neutrons, nuclei, electrons, and photons, even with the intense amounts of energy imparted to them, have to have their energy cascade and propagate through the entire outer layers of the star. As a result of this, the neutrinos become the first signals to escape and the first signal to arrive on Earth. With the energies that supernovae impart to these particles, on the order of around 10 to 50 mega-electron volts per quantum of energy, the neutrinos will move at speeds indistinguishable from the speed of light. Whenever the supernova actually occurs, or occurred, which could have been any time from the 14th century onward, it will be the neutrinos that arrive here on Earth first, some 640 years later. In 1987, a supernova from 168,000 light-years away wound up creating a signal of a little over 20 neutrinos across 3 small neutrino detectors that were operating at the time. There are many different neutrino observatories in operation today, much larger and more sensitive than the ones we had at our disposal 33 years ago, and Betelgeuse, just 640 light-years away only, would send a signal some 70,000 times stronger on Earth due to its close proximity. In 2024, if Betelgeuse were to go supernova, our first surefire signature would come in the form of high-energy neutrinos, flooding our neutrino detectors all over the world in a burst spanning some 10 to 15 seconds. There would literally be millions, perhaps even tens of millions of neutrinos, picked up all at once by these observatories. A few hours later, when the first energetic ripples created by this cataclysm reached the star's outer layers, a breakout of photons would reach us, a swift spike that increased Betelgeuse's optical brightness tremendously. All of a sudden, the luminosity of Betelgeuse would spike by about a factor of 7,000 from its previously steady value. It would go from one of the brightest stars in the night sky to the brightness of a thin crescent moon, about 40 times brighter than the planet Venus. That peak brightness would only last for a few minutes before falling again back to being just about 5 times brighter than it previously was. But then, the traditional supernova rise begins. Over a time period of approximately 10 days, the brightness of Betelgeuse will gradually rise, eventually becoming about as bright as the full moon. Its brightness will surpass all the stars and planets after about an hour, will reach that of a half moon in 3 days, and will reach its maximum brightness after approximately 10 days. To skywatchers across the globe, Betelgeuse will appear to be even brighter than the full moon, as instead of being spread out over half a degree like the full moon, all of its brightness will be concentrated into a single, solitary, saturated point. As a Type 2 supernova, Betelgeuse will remain bright for a very long time, although there are large variations within these classes of supernovae for exactly how bright they become and how bright they remain over long periods of time. The supernova, after reaching maximum brightness, will slowly begin to fade over the time span of about a month, becoming about as dim as a half moon after 30 days' time. Over the next 2 months, however, its brightness will plateau, becoming dimmer only to instruments and astrophotographers. The typical human eye will not be able to discern a change in brightness over this time. All of a sudden, though, the brightness will drop precipitously over the next 4th month since detonation. It will go back to barely being brighter than Venus by the end of that time. And finally, over the next year or two, it will gradually fade out of existence, with the supernova remnant visible only through telescopes. At peak brightness, Betelgeuse will shine approximately as brightly as 10 billion suns, all packed together. By the time a couple of years have gone by, it will be too faint to be seen with the naked human eye. The reason the supernova remains so bright for the first 3 months or so isn't even from the explosion itself, but rather from a combination of radioactive decays, from cobalt, for example, and the expanding gases in the supernova remnant. During those first 3 months or so, Betelgeuse will be so bright that it will be clearly visible during the day as well as the night. Only after the 4th month or so will it become a nighttime-only object. And as it begins to fade from its brightness to look like a normal star once again, the extended structures should remain illuminated through a telescope for decades, centuries, and even millennia to come. It will become the closest supernova remnant in recorded history, and will remain a spectacular sight and astronomical object of study for generations to come. Whenever Betelgeuse finally does go supernova, and it could be tonight, next decade, or 100,000 years from now, it will become the most witnessed astronomical event in human history, visible to nearly all of Earth's inhabitants. The first signal to arrive won't be visual at all, but will come in the form of neutrinos, a typically elusive particle that will flood our terrestrial detectors by the millions. After that, a few hours later, the light will first arrive in a spike, followed by a gradual brightening over a little more than a week, which will fall off in stages over the coming months before gradually declining for years. The remnant, which consists of gaseous outer layers illuminated for thousands of years, will continue to delight our descendants for generations to come. We have no idea when the show will begin, but at least we know what to look for and expect when it actually occurs. At that time, hope that our time machine, the James Webb Space Telescope, can capture some breathtaking images of stunning scenes that only happen once in a lifetime. The arrival of the cutting-edge James Webb Space Telescope has revealed the structure of the iconic supernovas in greater detail than ever before. For instance, just a few weeks ago, James Webb spotted the remains of a supernova explosion in a new light. The remnants, called Cassiopeia A, or Cas A for short, lie 11,000 light-years from Earth in the constellation Cassiopeia. In April of this year, Webb imaged the stellar remains in mid-infrared light. Now, the newly released snapshot shows Cas A's colorful, orb-like wisps captured using James Webb's NIR cam. The light from Cassiopeia A's explosion reached Earth about 340 years ago. Scientists estimate that in its early days, the star that yielded the explosion had a mass 16 times that of the Sun, but it shrank to about 5 times the size of the Sun before it blew. Since the explosion occurred thousands of light years from Earth, it took thousands of years for its light to reach us. Previously, the Hubble Space Telescope, Spitzer Space Telescope, Chandra X-ray Observatory, and other telescopes had imaged Cass-A Chandra's study, revealed the amounts of different elements produced by the explosion. The supernova has spat out 10,000 house times the mass of the Earth in sulfur, 20,000 times Earth's mass in silicon, 70,000 Earth masses of iron, and 1,000,000 Earth masses of oxygen. Webb's NIR cam detects wavelengths of light that are broader than visible light, and thus can't be seen by the human eye. So, to compose the new image, researchers translated the infrared light in different colors. The bright orange and light pink areas in the new image represent the supernova's inner shell and are made up of sulfur, oxygen, argon, and neon from the star. Dust and molecules that will one day form new stars are in this gas. As that dust cools, it glows. This light echo, nicknamed Baby Cass-A, is about 170 light-years behind the main supernova remnant. Beside James Webb, a new search for supernova remnants in our galaxy is underway. Scientists are aiming to find hundreds of these star explosion remains scattered across the Milky Way by using radio observations captured with the Very Large Array in New Mexico and the Meerkat Array of radio telescopes in South Africa. A supernova, as told, is a destructive stellar explosion, either of a massive star at the end of its life or a white dwarf that has accumulated too much stolen matter on its surface, taken from a companion star, and undergoes a thermonuclear explosion. Either way, the star or white dwarf is blown to smithereens, its guts strewn across space to form a supernova remnant. This debris contains many heavy elements formed in the violence of the supernova explosion, and at the leading edge of these remnants are shock waves that initially move at perhaps 10% of the speed of light. Long after the light of the supernova has faded, this expanding remnant of gas and dust lingers for hundreds of thousands of years, gradually slowing its expansion as it disperses into the interstellar medium. Between 300 and 400 supernova remnants have so far been found in our Milky Way galaxy. Some of these are sure things, including the Crab Nebula, the Veil Nebula, the Vela supernova remnant, and the Cassiopeia A supernova remnant, which is about 330 years old. The youngest known supernova remnant in our galaxy is G1.9 plus 0.3, which is found in the Milky Way's inner portion and is about 130 years old. However, observations of other galaxies find that these other realms are home to many more supernova remnants than are known in our galaxy. And based on the number of remnants in those nearby galaxies, astronomers reckon there should be as many as 1,000 in our galaxy, meaning there are likely many still to be discovered. Now, West Virginia University professor of astronomy, Lauren Anderson, is on a hunt for those yet-to-be-found star explosion remains. There is a severe discrepancy in the number of supernova remnants we would expect to see compared to the relatively low number we have detected, said Anderson in a statement. With a grant of $331,170 from the National Science Foundation, Anderson and West Virginia University graduate student Timothy Fairber will use the Very Large Array and Meerkat to search for radio emissions stemming from hidden supernova remnants. They plan to employ machine learning as well as the visual inspection of digital sky images to try and distinguish them from other forms of nebulosity in the galaxy, such as star-forming H2 regions of molecular hydrogen. In particular, Anderson and Fairber will direct their search towards the galactic center, where the high density of stars increases the chances of finding recent supernova remnants. Plus, they aim to not only find new remnants, but also to confirm whether objects suspected of being remnants indeed are, and to rule out any H2 regions that have been misidentified as supernova remnants. According to Anderson, this study is timely. Recent data from Meerkat allow for the most sensitive search for supernova remnants yet, and recent works have identified hundreds of possible supernova remnants that need to be confirmed. Finding the remnants isn't just an exercise in cataloging them. They are all important to study. For example, the shape of a remnant and the distribution of its elements can allow astronomers to create 3D simulations depicting how a supernova ejects its debris, how that debris interacts with the interstellar medium, and ultimately, how the debris ends up in gas clouds that form the next generation of stars and planets. In another remarkable finding, scientists just stated that we may be closer than ever to cracking the mystery of what lies deep beneath the surface of dead, ultra-dense stars called neutron stars. A new supercomputer analysis of neutron stars has revealed that there's between an 80% and 90% chance that these bodies have cores packed with free quarks, which are fundamental, subatomic particles usually only found bound together in other particles like protons and neutrons. Protons and neutrons themselves come together to form the nuclei of atoms, around which electrons reside. But according to the team, if neutron star cores are indeed full of free quarks, they'd be composed of an exotic form of matter known as cold quark matter. And in cold quark matter, individual protons and neutrons cannot exist. So, atoms cannot exist, only the quarks. If true, this would make neutron stars akin to incredibly enormous atomic nuclei. As research lead author Jonas Nettila, who is about to take over as associate professor at the University of Helsinki, said in a statement, "It is fascinating to concretely see how each new neutron star observation enables us to deduce the properties of neutron star matter with increasing precision. Neutron stars are born when stars with masses between 10 and 20 times that of the Sun run out of the fuel necessary for intrinsic nuclear fusion occurring in their cores. This results in the cessation of the outward energy that for millions or even billions of years has held the star stable against the inward pressure of its own gravity. With gravity the victor in this cosmic tug-of-war, a star's core begins to collapse. As this happens, the outer material of the star, where nuclear fusion is still taking place, gets blown away in a massive supernova explosion. This leaves the stellar core with a mass between 1 and 2 times that of the Sun, condensed down to a width of only around 12 miles, 20 kilometers. This massive reduction in the size of what is now a neutron star creates matter that is so dense a mere sugar cube-sized block of it would weigh around 1 billion tons if brought to Earth. That's a sugar cube that weighs as much as 3,000 Empire State Buildings. So now the question is, what is this incredibly exotic matter, probably found nowhere else in the universe, made of? And, more generally, can the conditions at the densest regions of these dead stars really create an entirely new phase of matter called cold quark, matter void of protons and neutrons? Scientists can't visit neutron stars to get a sample of this material. Even the closest neutron stars are around 400 light-years away. So the next best thing is to simulate the conditions beneath the star's surfaces using a powerful combination of actual astronomical data and supercomputers. This new research used a type of statistical deduction called Bayesian inference that calculates the likelihood of different model parameters by making direct comparisons with observational data. This allowed the team to determine the boundaries for neutron star matter, leading the crew to conclude the presence of cold quark matter to a high degree of probability. The mechanism also suggested a state of matter exists in neutron stars that is non-nuclear, in which quarks are allowed to exist, deconfined in protons, neutrons, and other particles. Their constituent quarks and gluons are instead liberated from their typical color confinement and are allowed to move almost freely, said Alexei Vorinin, a professor of theoretical physics at the University of Helsinki. The team's supercomputer simulations also suggest a below 20% probability that matter within neutron stars experiences a rapid state change from nuclear matter to quark matter, almost like water changing to ice. Such a quick change in matter could destabilize neutron stars in a way that could make even a tiny quark matter collapse to birth a black hole. The research also offered that the existence of quark matter cores could be fully confirmed in the future with some further analysis. The key to this would be to determine the strength of the phase transition from nuclear matter to quark matter, something that could be possible when gravitational wave detectors become sensitive enough to hear. Tiny ripples in space at times stemming from the last moment before two neutron stars orbiting one another collide. Nonetheless, even with improved observational data, better models of neutron star cores will still require a vast amount of computational power and time. As Jonas Hirvonen, team member and a graduate student at the University of Helsinki, said in the statement, "We had to use millions of CPU hours of supercomputer time to be able to compare our theoretical predictions to observations and to constrain the likelihood of quark matter cores." James Webb, once again, requires scientists to rethink our understanding of the universe. In the latest discovery, the telescope has just detected a key building block of life at the dawn of the universe, upending what we know about the first galaxies. The discovery, a cloud of carbon in a distant and compact galaxy as it appeared just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. The results have been accepted for publication in the journal Astronomy and Astrophysics, and a preprint version can be found on AR-Archive. As co-author Roberto Maiolino, a professor of experimental astrophysics at the Kavli Institute for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang, but we found that carbon formed much earlier. It might even be the oldest metal of all." Astronomers classify elements heavier than hydrogen and helium as metals. That's because, aside from hydrogen and trace amounts of lithium, these elements were forged inside the fiery furnaces of stars and distributed throughout the universe by star explosions called supernovas. This process of heavy element production and seeding was once thought to take many star lifetimes before elements heavy enough to form planets were widely available. But new discovery made by James Webb has challenged this preconception. What James Webb found in the remote galaxy known as GSZ-12, which was 100,000 times less massive than the Milky Way, were traces of oxygen and neon mixed with a strong signal of carbon. Exactly how carbon could have formed so early in the universe's life is unclear, although it could be due to stars collapsing with less energy than initially thought, according to the researchers. As carbon would have formed in the star's outer shells, this could have enabled it to escape and seed the early universe sooner than expected, instead of being sucked inside the black holes formed from the collapsing stars. That means it's not necessarily true that life must have evolved much later in the universe. Perhaps life emerged much earlier. Perhaps somewhere, under some conditions we might even consider too exotic for life, there are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. At that point, it simply becomes a game of hide and seek. Where is everybody? Why haven't we made first contact with aliens yet? This question is known today as the Fermi paradox, and it has had astrobiologists and other scientists scratching their heads for ages. First off, if we want to understand how the universe makes intelligent life, we have to consider two things. First, we have to consider the steps that needed to occur in order to bring about our own existence. And then, we need to think about ways that intelligent life could arise in circumstances that differ from our own, and to make sure, wherever possible, that we're doing it in as quantitatively accurate a fashion as possible. We also have to make sure that we don't make unfounded assumptions or fall for any one of a number of logical fallacies, like conflating absence of evidence with evidence of absence, or the post hoc ergo propter hoc fallacy. It's also important to learn how not to estimate what's out there. There are two all too common mistakes that people, even the most brilliant of scientists, make when considering this question. One is that they make point estimates akin to, we may not know this parameter, so here's what we estimate it to be, which is relatively meaningless. If you're going to make such an estimate, it's only meaningful if you include an uncertainty range, a set of error bars, or some other likelihood predictor. There's an enormous difference between saying that you estimate the odds of something to be 1 in 100 with a 10% uncertainty, a 1,000% uncertainty, or a two-tailed uncertainty, where it could be as high as 1 in 10, but there could be no lower limit at all. However, the other mistake that people make is perhaps the most common of all when it comes to attempting to answer the Fermi paradox, making use of the Drake equation. The Drake equation yields many interesting lessons, and when it was first put forth, it was a monumental achievement from a scientific perspective. For the first time, it broke up a seemingly unknowable question of how many intelligent, spacefaring civilizations there are within our galaxy today into a series of smaller questions that we could conceive of solving one at a time. For example, we could measure or estimate things like the rate of star formation in the Milky Way, the share of stars that have planets, the average number of potentially life-supporting planets around stars with planets, the fraction of planets that could have life that actually wind up with life, the fraction of planets with life that go on to develop intelligent life, the fraction of intelligently inhabited planets that emit detectable signals, or the length of time that such civilizations continue to emit those signals. When you multiply all of those things, you'll wind up with an estimate for the number of active civilizations that we could potentially detect today. But immediately, we run into a few major problems. For one, we've measured the rate of star formation in the Milky Way, and we actually know it pretty well. Unfortunately, if you took that star formation rate and multiplied it by the age of the universe since the hot Big Bang, you'd wind up with almost no stars. You'd calculate that the Milky Way should have formed a total of around 10 billion stars over our cosmic history. I know that 10 billion probably sounds like a big number, but compared to the actual estimate for the number of stars in our galaxy, which is more like 400 billion, it's only 2 to 3%. Fortunately, it's easy to identify why this method of calculating how many stars we've formed, which you'd imagine would give you the total number of stars in the galaxy, is so thoroughly wrong-headed. The superficial reason is fairly obvious. The star formation rate is not constant over our cosmic history. In fact, we've come to understand that the universe was born without stars, which began forming during the first 200 million years or so. We've learned that star formation increased for the first 3 billion years of our cosmic history, reached a peak, and has been dropping ever since. Locally, we've probably experienced bursts of star formation when we've absorbed smaller satellite galaxies. And we might even be starting to experience another burst as the Magellanic Clouds and Andromeda exert their gravitational influence on the gas, dust, and other neutral matter within our own galaxy. But that's only the superficial reason why the Drake equation is problematic today. The deeper reason is that the Drake equation, when it was put forth, made an assumption about the universe that we now know is untrue. It assumed that the universe was eternal and static in time. As we learned only a few years after Frank Drake first proposed his equation, the universe doesn't exist in a steady state, where it's unchanging in time, but rather has evolved from a hot, dense, energetic, and rapidly expanding state. A hot Big Bang that occurred over a finite duration in our cosmic past. Instead, a much more productive route is to calculate the quantities we now can speak about with some level of certainty, and then move on to the great cosmic unknowns in as responsible a fashion as we can. Unlike the situation some 60 years ago, when the Drake equation was first proposed, we now have an excellent idea of what our universe is like, both in and beyond the Milky Way and the local group. We understand what the various populations of stars are that exist, and what sorts of steps need to occur to make heavy elements, rocky planets, and allow for the possibility of complex chemistry and important reactions, such as the formation of energy-storing molecules from nothing more than the ubiquitous building blocks and starlight. We've also learned a lot about the types and abundances of planets that exist around stars other than our own, exoplanets. As recently as 30 years ago, we were only discovering our very first planets around stars besides the Sun. At the end of 2021, we're closing in on a whopping 5,000 confirmed exoplanets. And sure, there are biases in our data. We're preferentially detecting the planets that are the easiest to detect. But we know how to account for those biases. Instead of needing to speculate about how many stars form, how many have planets, how many planets per system have the potential for life, we can actually utilize some excellent data. Here in our modern Milky Way, we already know how many stars there are, how those stars are divided into different populations, how many planets there are per star, how many of those planets have the right composition of elements to lead to complex chemistry, and how many of those planets have the potential for hosting life. On this front, it's actually straightforward to come up with a solid estimate for how many potentially habitable planets are in our galaxy. In fact, we can perform that calculation in a variety of ways, just to show the power of our set of knowledge. Of the approximately 400 billion stars in the Milky Way, about 80% are red dwarfs, or 18% are like the Sun, and only 2% are too massive and short-lived to be interesting for life. As far as we can tell, there are about 5 to 10 planets per stellar system, with approximately 1 to 2 planets in what we call the habitable zone around each star. Of the planets that exist around Sun-like stars, we believe that 20% of them are Earth-like in terms of size. A greater percentage than that are terrestrial around the more common red dwarf stars. If we assume conservatively that red dwarf systems are not habitable at all, but Sun-like systems are, then all we have to do is multiply the following figures. The number of stars, 400 billion. The proportion that are Sun-like enough to support life, 0.18. The number of expected potentially habitable zone planets per relevant star, 1.5. The fraction of those planets that are Earth-like in size, 0.20. We then derive an estimate for the number of potentially inhabited planets in the Milky Way, 21,600,000. It doesn't make sense to use so many significant figures. 20 billion is good enough. But also, we have to remember that all of these numbers have uncertainties. There may be as few as 200 billion stars, half of our estimate. Some of the stars may be too low in metals, what astronomers call the heavy elements in the universe, for planets to support life, but the percentage is small, less than 10% for certain. Some stars might not have planets, but again, the percentage is small, less than 20% for certain. The habitable zone may be larger or narrower than we think. Tack another 33% uncertainty onto our estimate. And we haven't sampled the low end of the mass radius portion of the exoplanet population very well. Our estimate of 20% being Earth-like in size could go up or down, so it's reasonable to put a 25% uncertainty on that figure. All in all, there could reasonably be as few as 5 billion potentially habitable planets in the Milky Way, or perhaps as many as 50 billion. If red dwarf systems are potentially habitable as well, that number could increase tenfold. And at the same time, many of the things we've worried about in the past likely don't particularly matter one way or the other, such as whether a planet has a major moon or not, whether it has a Jupiter-like world in its stellar system, whether it's located close to or far from the galactic center, and whether it's a part of a singlet or multi-star system. But beyond that, we still have some major unknowns where our level of cosmic ignorance is truly staggering. We know the ingredients that life requires are ubiquitous everywhere we look. In asteroids, in gas in the galactic center, in outflows around massive, newly forming stars, and even in the atmospheres and on the surface of other planets and moons in our solar system. But even with all the raw ingredients, what is the fraction of potentially inhabited planets where life actually arose from non-life? In Carl Sagan's original Cosmos series, he gave a figure of 0.10%, and asserted that this was a conservative number. That is not necessarily the case. Life could be difficult. Just because it arose early in the history of Earth doesn't mean that a significant fraction of planets actually have or ever had life on them. It could be nearly 100%, or 10%, or 1%, or 0.01%, or a 1 in a million chance that life arises from non-life. So if we rewound the clock and started Earth over again, how likely is it that life would have arisen and thrived here? Well, our ignorance is astounding. Similarly, once life does arise, how often does it get wiped out, versus how often does it endure for many billions of years? How frequently does it remain in a relatively simple state, unable to develop complexity, differentiation, multicellularity, or sexual reproduction? How often, even after billions of years, does it actually begin to look like life on Earth at the start of the Cambrian explosion? Again, we have no knowledge at all about how this might work. If you estimated that it occurred 10% of the time, that's reasonable. But so is 90% of the time. So is 0.001% of the time. Without observational or experimental evidence to point us in the right direction, we're simply deluding ourselves if we make a strong assertion. Furthermore, we know that after life on Earth became complex, differentiated, multicellular, and sexually reproductive, it still took more than 500 million years for a species to arise that would become technologically advanced, and that was likely just the result of random chance. How often does that occur? Does it make sense to represent this probability in percentages, or is this such a rare event that it's like winning the Powerball lottery 5 times in a row? Furthermore, how long does that technologically sophisticated life endure? Does it ever become a multi-planet or even an interstellar civilization, or is the progression from technologically advanced to extinct a relatively rapid one? At this point, our uncertainties are so large that it's eminently reasonable that not only might human beings be the only intelligent life in the Milky Way, but in the entire observable universe, which likely contains more than 1 trillion times as many stars as our own galaxy. We can confidently say, give or take, that there are perhaps 20 billion Earth-sized planets made of similar elements to our own world, at the right distance from their parent star to have liquid water on their surface, assuming an Earth-like atmosphere as well. But of those worlds, how many of them have life? It could be most of them, many of them, or only a tiny fraction. Of the ones with life, how many of them develop complex, differentiated, intelligent, and technologically advanced life? Before we even start asking questions about longevity, colonization, or machine-based life, we should admit, with a non-negligible probability, the most obvious resolution to the Fermi paradox. The reason we haven't made first contact with intelligent, technologically advanced, and spacefaring alien civilizations is because there are none. In all the galaxy, and perhaps even in all the universe, we really may be alone. Without evidence to the contrary, we have every reason to keep looking and searching, but still no reason other than our own preferences to believe that other creatures, similar to humans, exist out there. While it may be incredibly fun to theorize a myriad of possible explanations as to why intelligent extraterrestrials might remain hidden from us, the simplest possibility, that they just aren't out there, should be the default hypothesis until proven otherwise. What's notable, in addition to upend what we know about life in the universe, James Webb is also providing science with a further gift. Detecting exoplanets used to be so difficult that scientists spotted the first black hole, detected the leftover radiation from the Big Bang, and took snapshots of countless distant galaxies before discovering the first planet beyond our solar system in 1992. Plenty of exoplanet astronomers began their careers before the field of exoplanet astronomy even existed. But now, astronomers have identified well over 5,000. And continue to find more. Given the stream of discoveries, it can be easy to forget how little we still know about these distant worlds. The colorful volcanoes, oceans, and cloud-streaked atmospheres that appear in artists' renditions are speculative fantasies often inspired by the only information scientists have about most worlds: their mass, radius, and distance from their star. But the James Webb Space Telescope is revealing exoplanets in dazzling new detail. Scientists are using the telescope, launched at the end of 2021, to study the atmospheres of hundreds of worlds, from gas giants to rocky worlds about the size of Earth. As an exoplanet orbits its star, starlight passes through the planet's atmosphere, and light at specific wavelengths is absorbed depending on the gases present. This leaves traces in the spectrum of starlight, which scientists can use to figure out which chemicals the light passed by. James Webb is sensitive to infrared wavelengths where these traces are strongest and has already detected water, carbon dioxide, methane, and more on other worlds. That means Webb's planned 10-year lifetime could reveal a lot, perhaps answering fundamental questions including what exoplanets are made of, how they form, and whether our solar system is an oddball within our galactic neighborhood. Here are 5 big planetary puzzles that scientists hope to solve with James Webb. 1. Why do some rocky planets have atmospheres and others don't? If a rocky planet is going to host life, it needs an atmosphere. But scientists still aren't sure what determines whether a rocky body can hold on to a gaseous outer shell. Astronomers are searching for what they call the cosmic shoreline, a conceptual dividing line that separates worlds with and without atmospheres. In 2017, scientists identified such a shoreline within our solar system, set by the balance between the amount of radiation a planet or moon receives from the sun and the strength of the world's surface gravity. Sunlight provides gas particles with the energy needed to escape from the upper atmosphere, while gravity holds atmospheric gases to the planet. To test whether this type of cosmic shoreline exists throughout the galaxy, scientists need to figure out which exoplanets have atmospheres and which don't. This question may sound incredibly basic, but it's only just now becoming possible to answer thanks to James Webb. Renyu Hu, an astronomer at NASA's Jet Propulsion Laboratory in Pasadena, California, says he and colleagues have settled the atmosphere question for 55 Cancri E, a planet that orbits a sun-like star some 40 light-years from Earth. 55. Cancri E is a super-Earth, a bit bigger than Earth but much smaller than Neptune. In a paper published May 8 in Nature, Hu and colleagues present Webb's data, suggesting that 55 Cancri E has an atmosphere of either carbon monoxide, carbon dioxide, or a mix of the two with nitrogen. It's the first detection of an atmosphere shrouding a terrestrial or rocky exoplanet. But scientists are pessimistic about the existence of atmospheres on the other rocky worlds James Webb is observing, specifically those orbiting M-dwarf stars. These small, dim stars are easiest for James Webb to see. They also tend to spew bursts of atmosphere, stripping radiation more often than stars like our Sun. So some scientists doubt that rocky planets around these stars can hold onto atmospheres. According to James Webb observations of LHS 3844b, a super-Earth orbiting such a star, the planet is almost certainly a bare rock. Webb's observations of the planets TRAPPIST-1b and TRAPPIST-1c, which orbit the M-dwarf TRAPPIST-1, suggest that these planets are bare too. But it's also possible that they could have very thin atmospheres, says astronomer Elsa Ducrot of the Paris Observatory. Follow-up work with James Webb will help settle the question. As scientists use the observatory to identify more examples of rocky planets with and without atmospheres, our understanding of the cosmic shoreline can be put to the test. 2. What is exoplanet geology like? Discovering exoplanets without atmospheres also will allow astronomers to study something impossible to probe directly before James Webb: exoplanet geology. Scientists plan to use James Webb to look for the chemical fingerprints of specific rocks in the infrared light cast by the rocky, airless super-Earth LHS 3844b. Learning what the planet's surface is made of would be a powerful clue about the planet's geologic history and ongoing processes. Finding signs of granite would be especially intriguing. Granite is a common rock on Earth that forms from recycled and remelted rock. On Earth, this process depends in part on plate tectonics. But beyond Earth, granite appears to be vanishingly rare, probably because plate tectonics is too. Right now, there's no more evidence for plate tectonics on other worlds than there is for alien life. Thus, finding granite-like rock on an exoplanet would be a major discovery. 3. What are rocky exoplanets made of? While James Webb will help astronomers learn about the surfaces of exoplanets, it also might offer a glimpse at their geologic guts, thanks to a particularly extreme type of terrestrial world. Hotter than scorched Mercury, lava worlds orbit so close to their stars that their years are best measured in hours, not days or months. This proximity causes the planets to become tidally locked, meaning the same side of the planet always faces its sun. As a result, one hemisphere freezes in endless night while the other's rocky surface melts into lava. The magma oceans on the day sides of lava planets offer about as close to a window into the interior of a planet as astronomers could hope to find. Gases escaping from the magma might give clues to the composition of the planet's deep interior, and learning what planets are made of can tell astronomers a lot about how these bodies form, and whether their compositions and histories are similar to or different from the way rocky planets form in our solar system. 4. Sub-Neptunes are the most common planets in our galaxy. What are they? While what we know about Earth, Mercury, and Mars can help astronomers imagine what alien rocky planets are like, the most common type of planet in our galaxy can't be found in our solar system. UB Neptunes, so named because the planet's radii are just a bit smaller than Neptune's, seem to be everywhere scientists look. But scientists still know very little about these worlds. For example, are they gas giants, rocky planets, or something else entirely? Based on their masses and radii alone, sub-Neptunes might be miniature ice giants rich in ammonia, methane, and water, like Neptune and Uranus. But the same data could describe planets with very different structures, such as rocky cores wreathed in hydrogen and helium, or exotic water worlds made mostly of different forms of water, not necessarily liquid. Using James Webb, scientists plan to study the atmospheres of sub-Neptunes to distinguish between these possibilities. Webb's observations of the sub-Neptune K2-18b made headlines last year after researchers detected carbon dioxide and methane, but no ammonia, an expected component of gas planets, in its atmosphere. The team interpreted this gas mix as evidence for a water world, since ammonia dissolves easily in water and would get trapped in an ocean if it were there. But other researchers think the same data could fit a Neptune-like composition with a thick gas envelope over a rocky core. A definitive answer will require follow-up observations. 5. How do gas planets form? Despite having 4 gas giants in our solar system, scientists still aren't sure how these enormous worlds form and evolve. How do gaseous planets form? How do they evolve? And what are they made of? These are fundamental questions in planetary science that scientists still haven't answered. In particular, scientists want to know whether gas giants form where we find them, or whether they tend to wander over time, as they seem to have done in our solar system. Planets can wander due to gravitational interactions with other objects, including the disks of gas and dust that orbit young stars and provide the raw materials for planets. Gas planet migration can wreak gravitational havoc, knocking other planets out of their orbits and flinging around small bodies like comets and asteroids. The resulting chaos can have serious implications for the stability and potential habitability of smaller worlds. James Webb could provide astronomers with a vital clue to this mystery: the composition of gas giant atmospheres. The abundance of elements heavier than hydrogen and helium in gas giant atmospheres should depend on where the planet formed relative to its star. In general, the heavier the elements found in an atmosphere, the farther out the planet formed. Observing enough gas giant planets to start identifying trends, and planets that buck them, could reveal the general rules governing how these planets form and migrate. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.